third video in Unit 5, where I'll be discussing how we can assess the position of equilibrium or the favorability of a SNAc reaction. So I'm showing you an example here of an ester reacting with NH2- as a nucleophile. And in essence, what we're trying to decide is, for this SNAc reaction, will the equilibrium constant be like larger than 1, in which case we would expect to see the products dominate at the end of the reaction? Is KEQ less than 1, or we would see the reactants left over at the end of the reaction? Or is KEQ essentially equal to 1, which would tell us that we've got about the same amount of product and reactant at equilibrium? So favorable, in quotes, is kind of a qualitative idea. No two people will necessarily agree on exactly what favorable means. For our purposes, we'll go ahead and make the assumption that a favorable reaction will have a KEQ that's greater than 1. So if that number is 2, that's not that favorable. If that number is 10 to the 20th, that's extremely favorable, but we're going to make an arbitrary cutoff. Favorable is greater than 1 for a KEQ. So how do we go about making a decision for a given SNAc reaction, for instance, this one, of what this KEQ should be? Well, it would be very difficult to actually do this numerically. Unfortunately, we don't have the ability to use, like, for instance, pKas in the same way that we did with acid-base chemistry, where we could calculate an equilibrium constant. But we could use structural analysis to make some decisions about which side would likely be favored. And that would give us some information about the value of KEQ in a qualitative sense. So one of our strategies is structural analysis. In which case we would want to focus on the actual structures of the reactants and the products to make some decisions about, well, which set of materials is more stable. So just like we dealt with acid-base chemistry, we're looking for stabilization of structures. We know that nature will typically, in the absence of other competing factors, try to make compounds that are more stable from compounds that are less stable. So we're going to be seeking structural stability. We will be seeking that in our analysis because that's what nature is seeking when these reactions are actually happening. Now, there's a variety of ways that we could assess this. We could look at the carbonyls themselves, for instance, or we could look at the anions here, or we could look at both of these compounds and both of the other compounds. But the key with any kind of analytical technique is you want to try to control as much as possible so that you're making clear, clean comparisons. Otherwise, it's very difficult to make decisions. But we know that we can do the structural analysis in a couple of ways. We can focus on like structures compared to like structures, and that gives us choices. We can either compare our nucleophile, which is probably the NH2 group here, to our leaving group, or what we've been calling our Y group, because both of those compounds appear to have an excess of electron density. And moreover, if we look carefully at this reaction, we can see that there are 2 lone pairs on the nitrogen here, and only 1 on that same nitrogen in the product. On the other hand, there were 2 lone pairs on the oxygen, the leaving group, in the reactants, and there are 3 lone pairs on that same oxygen in the product. So a SNAc reaction, among other things, looks like transferring a lone pair from the nucleophilic site onto the atom that's part of the leaving group. So we can focus on, as one option, comparing nuke to our leaving group, and specifically the leaving group once it's in the products. What we're looking for is stabilization of that lone pair that seems to be transferred. So whichever side has a more highly stabilized lone pair among these structures, we know that side is going to be favored. This probably sounds a little familiar. This is essentially the same framework we used to start talking about acid-base chemistry. We were talking about, well, if you've got a base and a conjugate base, and you're assessing acid-base equilibrium, you're looking for which of those structures is more stable. Same idea here. We're looking for, if we're comparing the nucleophile to the leaving group, which of these sets of lone pairs, like for instance maybe this one versus this one, would be more stable. If we know that going from nitrogen onto oxygen as a lone pair, if that's going to be stabilizing, then this reaction is going to proceed in this direction to access those stabilizing features. If the reverse is true, the reaction goes back that way. What's left for us to do then is implement our set of structural tools of things like electronegativity and atomic radius and resonance and induction to make these kinds of decisions. So the tools are exactly the same. The only thing that's changed is a small tweak to our framework. Now we're analyzing a totally different kind of reaction. This is not acid-base chemistry. This is a SNAc reaction. But we're looking at anion stability because that seems to still be relevant to this particular kind of a process. So let's actually implement our analysis in this example problem using our framework here. We know that the nitrogen has a few things going for it. Nitrogen is relatively electronegative. Certainly more so than a carbon or a boron atom or an iodine or something like that. It's relatively small. I'm going to put small in quotation marks. It's like a second row element, not like sulfur or selenium or phosphorus or something like that. I don't see any inductive effects because there's really just hydrogens attached to the nitrogen here. So I've got no induction. And I don't have any conjugation or resonance. Okay, so I've done an assessment using all 4 of my tools for this nitrogen. I know that the lone pair here is like kind of stabilized by electronegativity, and none of these other features really matter much for me. Now let's do the same analysis for the oxygen in our leaving group. So oxygen is, and this is critical, more electronegative, right? I'm comparing 2 things. So these qualifiers like more or less, stronger or weaker, those are really helpful when I write down my decisions. It's about the same size. Oxygen is a very little amount smaller than nitrogen, but not necessarily a big deal. It's also small. There's no real induction to speak of. I have a methyl group here. And finally, I don't see any possibility for resonance. The carbon in the methyl group has no p orbitals. I'm not going to be able to draw any resonance structures here. So on the basis of my decision making, it looks like the only point of difference is electronegativity. And that's going to be sufficient for me to actually point out that this oxygen anion is more stable, or at least the lone pair on oxygen is more stable than that on nitrogen. And that should mean that this reaction is actually favorable. So from this set of assessments, we could say that KEQ is going to be greater than 1. So that's how we could actually implement structural analysis here. You might also think about what you know that could be experimentally measured about this concept of lone pair stability. That sounds a little bit like it's related to pKas. Remember we said that compounds that have those highly stabilized lone pairs on conjugate bases, that those structures tend to be fairly strong corresponding acids. In other words, that's the correlation you developed in Unit 2. It turns out that we could also, rather than doing this structurally just by using our 4 tools, we could also look at pKas of conjugate acids. So pK, this is important, Ca, conjugate acids, I'm going to make the C red, not the A though, C, conjugates, A. And we know that this is going to correlate such that whichever side has the more acidic conjugate acid, that's going to correspond to a more stabilized lone pair. So more acidic equals side that's favored in a SNAc reaction. Be clear what we're analyzing here. A SNAc reaction, not an acid-base chemistry reaction. Okay, so let's implement that same concept for our example problem. We already made a decision about the relative magnitude, I guess greater than 1, for KEQ. We can do the same thing here, but these are not structures of conjugate acids. I need to actually know what the conjugate acid structures are. So first I'm going to draw my conjugate acids. That's going to be adding a proton to this compound. That gives me ammonia. And then if I do the same thing with OMe minus, that's going to give me methanol. So those are the structures of my conjugate acids, right? If this compound lost its proton, it would become this thing. That is the relationship that we're exploiting. So I know that a pKa for something like an amine is about 35. And we know that the pKa for methanol and alcohol is about 15. Okay, so what does that tell us? Well, the conjugate acid of our leaving group is much more acidic than the conjugate acid of our nucleophile. That means that this nucleophile has a less stable pair of electrons than this did. Same decision we made using our 4 tools, but now we can also use pKa data where it's available to either make the consideration initially or to support what we think might be true on the basis of structural analysis. But of course, there's another way to do this. Instead of looking at the nucleophile in the leaving group, we could look at the carbonyl reactant versus the carbonyl product. So that would be another likes comparing to likes kind of assessment. For ease of discussion, I'm going to number the reactant carbonyl compound 1, and I'm going to call the product carbonyl compound 2. So compound 1 is an ester, compound 2 is an amide. And in this case, we can compare the electrophilicity, the relative electrophilicity of the carbonyls. And in particular, the side of the equilibrium with the less electrophilic carbonyl will be favored. Okay, why would that be? That the side with the less electrophilic carbonyl would be favored? Well, we could think about the SNAc reaction that's reversible as essentially 2 different SNAc reactions that are running in opposite directions. One is that our ester group is reacting with an NH2- nucleophile to make products. That's going to have a particular rate. The rate of that reaction will go up as this compound becomes more electrophilic. On the other side, we have an amide reacting with OMe-. And so that reaction will also have a rate. That rate will go up as the carbonyl becomes more electrophilic. So what if the reaction running to the right is faster than the reaction running to the left? That means you have an imbalance, and as those 2 reactions are happening simultaneously, we start moving toward the products to the right because there's essentially rate pressure to go this direction. And that's going to correlate with electrophilicity. What we know from both half-life data as well as all of our analysis from unit number 4 is that this ester is far more electrophilic than an amide. And you'll notice I didn't say that an ester is a good electrophile or a bad electrophile because I don't care. All I care about is its electrophilicity relative to what would be made in the SNAc reaction. So this is less electrophilic than our ester. Okay, that tells me that there's going to be a faster rate going this direction than this direction, which suggests that the products for this particular SNAc reaction should be favored. Well, that's exactly what I came up with, both by using pKas and by analyzing the structures of lone pair stabilities. All 3 of these methods, if used correctly, will tell you the exact same thing. There are 3 different ways of understanding something fundamental about what's happening in this reaction. In our first practice problem, we'll be looking at an acid chloride reacting with ethoxide, so notice the 2 carbons here, to form an ester and Cl-. So this looks like a pretty classical anionics type SNAc reaction. We can do this analysis in a few ways. Remember that we're going to be assessing what the estimated value of KEQ would be in a qualitative sense, so greater than 1, less than 1, or about equal to 1. We're going to use all 3 of our analytical techniques to actually answer this question, and all 3 of them should give me the same result. So let's use our pKa argument first, which means I'm going to have to do a couple of things. I'm going to have to draw the structures of conjugate acids of my nucleophile and the leaving group and the products, and I'm also going to have to assess pKa values for those conjugate acids. So here's my nucleophile, and it looks to me like this is going to be an alcohol group once I add a proton to the oxygen. Again, I'm not necessarily doing this protonation chemistry in the reaction. Drawing the structure of a conjugate acid is a way of making a decision. It's like a problem-solving strategy. So if I did the same thing here, I'm going to have HCl. Okay, so my pKa values for an alcohol, this is about 15. And HCl, we know, is a very strong acid. Its pKa is about -6. So if I look at this, it's telling me, these pKa values are telling me that this anion is more stable than this one. Right, and especially it's that lone pair that I'm focused on. So here I've got a less stable lone pair on oxygen. Again, it doesn't matter whether they're stable or unstable, it's about relative to each other. And that tells me that I'm going to favor the right-hand side in this reaction, or the KQ will be greater than 1. So that's our first assessment. We could also come up with the same conclusions we used pKa data to come to using structural analysis. So we could confirm oxygen is more electronegative than chlorine. It's definitely smaller than chlorine. Oxygen's in the second row. There's no real inductive effects that I'm worried about here. And it doesn't look like there's any resonance either. Remember that when I'm doing these two assessments, I'm analyzing the lone pair on the oxygen here. So I'm looking at what the ethyl group is doing to the oxygen. Not much. Yeah. Okay, same thing for chlorine. So chlorine is less electronegative than oxygen. It's definitely larger, third row. Chlorine is on its own in this anion, so by definition there can be no induction or resonance. We have no neighboring groups. Okay. So you can see why having this pKa method is helpful. To do this assessment qualitatively using structural analysis alone, I now have to decide which is more important, the change in electronegativity or the change in size. This is not a clean row or column comparison in the periodic table, it's a diagonal comparison. So we can see that based on the pKa data, it seems like maybe the size thing is more important than the electronegativity thing. But we wouldn't have necessarily known that without the actual data. And this is why it's important to solve these problems using all three of these different techniques, because it could be the case that one of them isn't that easy to implement while the other is. Just depends on the structures, right? All right, finally, we can do this via carbonyls. So in this case, we've got an acid chloride. And in this case, we've got an ester. So again, what we're looking for is which of those two carbonyl species is less electrophilic. That's the side that we're going to favor here. So to do that, we would need to do our structural analysis on the carbonyls, right? We don't necessarily have half-lives for all compounds. Notice that the cyclobutane group is the same in both cases, so I can ignore that. This sounds a lot like Unit 4 that we're coming back to. We're going to analyze the stuff that's changing in the boxes, right? The stuff that is our variable in terms of substituents for carbonyls. So we know that our chlorine group is going to be an inductive acceptor. We know that even though it has lone pairs to donate, it's a third row element, so that's going to be an exceedingly weak effect. Okay, and then if we do the same thing for our ester oxygen, we know that that's going to be an inductive acceptor also. Probably a slightly stronger one than the chlorine because of the oxygen's increased electronegativity. But we also know that that oxygen is a powerful resonance donor because it's a second row element that can donate into the carbonyl. So when I go to actually assess net effects, it looks to me like the chlorine is a net acceptor group, no resonance but inductive accepting, and the ester oxygen is probably a net donor because this resonance effect is likely going to be much more powerful than the inductive effect. And that's actually true. We did have half-lives for these kinds of functional groups. Remember, acid chlorides were the ones we could barely measure, and esters are on the order of like 2 years or so. depending on the structure of the ester. So we know that the ester is less electrophilic, and that means that the product side would favor that. In other words, that's like saying, well, O- minus is going to react faster with the acid chloride than Cl minus will react with the ester. That makes sense to me in my chemical intuition, which comes from these kinds of structural analyses. So all three of our methods predict the same thing. The equilibrium constant for this particular SNAc reaction should also be greater than 1. So here we'll look at a different kind of a SNAc reaction involving an amide electrophile and what we call a carboxylate nucleophile. So this is essentially like a deprotonated version of a carboxylic acid. And we're going to make a functional group that we've seen only in passing, an anhydride here. So there are 2 carbonyls with an oxygen that bridges them, and an N- as the leaving group in the products. Again, we're going to actually assess the equilibrium constant qualitatively using all 3 of our possible techniques. For consistency's sake, I'm going to keep doing them in the same order we did them in the previous example, but there's no reason why. That seemed what seemed right to me in the moment. You should always do all 3 while you're practicing to make sure you can do them all. And then whatever you like best or you think is most appropriate will be the tool you'll use on a homework or an exam, for instance. So we'll start by thinking about using pKas, and that requires me to draw conjugate acids. That means I need to know which structures to draw conjugate acids of, the nucleophile and the leaving group once it's left. So that means I'm going to add a proton to this oxygen. That's probably the place where a proton would go. Another way of saying that is this oxygen is the most basic site in this molecule. So we've got a compound that looks like this. This is a carboxylic acid, so its pKa is going to be around 5. And then I can do the same thing with this compound here. I don't have a lot of choices. I'm probably going to protonate the nitrogen. So I will have a compound that looks like this. This is an amine, so somewhere around 35 would be the pKa. And that tells me something really important. This anion is apparently much more stable than this one. That's what the pKas are indicating. So more stable anion. This is my less stable anion. It's a big difference. So if we do our structural analysis using our 4 tools, we should probably spot it right away. Well, we know that we've got an oxygen with a negative charge versus nitrogen carrying that new lone pair. So oxygen is more electronegative than nitrogen. Oxygen and nitrogen are about the same size. Oxygen is a little smaller. And here we see both some maybe inductive effect from this other oxygen, but more importantly, we notice that the oxygen of this carbonyl can serve as a resonance acceptor from this oxygen. And that will stabilize greatly the lone pair that's on this oxygen with a buildup of negative charge. So we've got resonance stabilization. And not only that, but it's resonance stabilization where the lone pair goes onto another oxygen, which is great because of the high electronegativity of oxygen. So I'm going to make sure I write that down. Once I've noticed that this oxygen is really involved in this resonance effect, it's fine. I can say, okay, it's also an inductive acceptor. That's definitely true. But it's almost sufficient because of the power of this resonance effect to kind of ignore the inductive feature of this oxygen, given this particular arrangement of atoms. So I'll say inductive acceptor as well. All right, now let's do this for our nitrogen group. So nitrogen is less, and then oxygen. It's a little bit smaller. I'm sorry, a little bit larger. About the same size though. Very similar. No resonance. So this carbon and this carbon, neither of them have p orbitals, and therefore there's no conjugated system here. No resonance. And I don't see any inductive effect either, just these hydrocarbons. No induction. So it looks to me like this deck is very heavily stacked in the favor of this particular placement of a lone pair. I get to be on a more electronegative atom that has extensive resonance stabilization from another highly electronegative atom versus being stuck on an isolated atom that's not even as electronegative as what I could choose if I stayed in the reactants. pKa data backs that up. This anion is far less stabilized than this one is, and that should tell me that this reaction runs to the left, that we have a fairly unfavorable SNAc reaction. KEQ will be less than 1. Okay, let's do this with carbonyls to confirm. So here we have an amide and an anhydride. The question arises with the anhydride, so which carbonyl should I be analyzing? My argument is going to be that we're going to trace, again, because we're trying to compare apples to apples as best we can, this carbonyl that was the electrophilic site in the reactants. We want to look at the same carbonyl in the products. So it would be the one that's attached to the methyl group still. This carbonyl is not really changing by nature of this reaction. It's almost a spectator to the bond forming and bond breaking in some ways. So this is a good place for you to practice what you learned in Unit 4 about analyzing relative electrophilicities of carbonyls. So please actually do the comparison of electrophilicity for the amide carbonyl versus the starred carbonyl and the anhydride using the tools that you know about, like resonance and induction. Once you've done that, you can actually check your work by seeing whether it would predict what we know would be true about the KEQ value for this particular SNAc reaction. So we know that the nitrogen here of the amide is a good resonance donor. And a moderate inductive acceptor. And certainly it's a not moderate, but weaker inductive acceptor than an oxygen here. Remember that the only thing that matters is what we're comparing, the structure to this one. We're not making any absolute assessments of reactivity. If we do the same kind of assessment for this oxygen, we see something kind of interesting. So we know that this is a better inductive acceptor for sure. We could make that argument purely on the basis of oxygen being more electronegative than nitrogen, as well as the fact that this oxygen has an inductive withdrawing effect from the carbonyl oxygen. So basically, we're making this oxygen even more powerful as an inductive acceptor than it otherwise would have been. This is kind of like an application of the concept that induction is additive. But we also know that the lone pairs on oxygen are actually kind of diluted. They do donate to the carbonyl we're analyzing, but they also donate to the other carbonyl. And that means that each carbonyl gets less electron density than it would if it was the only carbonyl in the structure. So here we've got an unusually poor oxygen donor, so poor relative to, say, like an ester, where there's just the one carbonyl. So we could say we've got a weaker resonance donor. And both of these effects together tell me that this nitrogen is going to be a much more powerful net donor than this oxygen will be. And that makes this amide less electrophilic than our anhydride carbonyl would be. It turns out that if we actually do half-life analysis for things like anhydrides, we find that they're only a little bit less reactive than acid chlorides. So half-lives on the order of still less than a minute, but maybe measurable in this case. And it's really kind of the case of this oxygen group, because of the presence of the other carbonyl, almost becomes a net acceptor on its own. So in a lot of ways, anhydrides and acid chlorides are kind of similar in their reactivity, which is useful for us. We'll see some cases where that can actually be quite helpful later in the unit. So if we have a less electrophilic carbonyl here on the left-hand side in our amide, in our reactant, then we would again expect the KEQ to be less than 1, which is good. That's consistent with the other results that we got from analyzing the nucleophile and lead group. So in the next section of this video, we'll look at a third example, but I'm going to actually just leave it blank and give it for you as practice. Let's look at one more example. You'll see that I've left this very bare bones, just the reactant structures here. What I'd like for you to do is practice everything that you've learned so far in this unit, where you'll actually predict the structures of the products of the SNAc reaction. That might require looking at roles. And then I want you to make the decisions about, given the structures you've come up with, whether the reaction is favorable or not. I'm actually not going to answer these questions in this video series, but rather I leave it up to you to use the discussion boards to discuss this with your peers about what kind of results you ended up with. Let's look at an example where we're using a neutral protic nucleophile, in this case an amine, reacting with an ester. So first we can practice figuring out what the structures of products would be. We know that this is our nucleophilic atom and this is our electrophilic atom, which I'm always going to try to note as I work through this. So here is our nucleophilic site, here is our electrophilic site, and it's likely going to be the case that the oxygen is going to serve as a better leaving group and everything attached to it than a carbon will. So this will be our leaving group here, whole thing, oxygen all the way up through the ethyl chain. And that means that our product will be an amide a so-called secondary amide, because we've got two non-hydrogen groups on the nitrogen, and we're also going to end up with an oxygen with an alpha group attached, but that oxygen is going to gain a proton. So we'll have ethanol. And lone pairs in. Okay. So in essence, one of these hydrogens is being transferred. The other is staying on the nitrogen. We can approach this in the exact same way that we approached the other kinds of SNAc reactions involving anionic nucleophiles. We can use structural stability arguments, we can use pKas for conjugate acids, or we can use assessment of carbonyl electrophilicity. So we'll do all three in this particular example. So let's look at our conjugate acid structures and the pKas of those conjugate acids. It would be very tempting, and it would be easy to do, to look at this structure and say, oh, well, I know the pKa of an amine, it's 35, and so that's the number I need to use. But remember, we're not actually talking about the pKa of the nucleophile, we're talking about the pKa of its conjugate acid, which means that we would actually need to consider the nitrogen that has gained a hydrogen, and we'll end up with 3 total. So that would be the conjugate acid that we need to care about. Remember, we're simulating the lone pair stability. We figure that out from looking at, well, how likely is it for this compound to lose a proton so that it has that lone pair? So this is an ammonium ion, pKa of around 10. We could do the same thing for our leaving group of the products. So again, it would be tempting to say, oh, alcohols, pKa 15. Again, that's not what we're trying to decide with. We need to know how stabilized one of these lone pairs is. To know that, we need to consider the conjugate acid of an alcohol itself. So add a hydrogen to the oxygen. We know that these protonated alcohols have pKas around 0. So when you're working through problems, if you elect to use the Pka strategy, which I think is a good one because you have a lot of Pka data at your fingertips, be careful about using it correctly, especially with these neutral protic nucleophiles, where you're assessing the correct structure. Remember to assess the conjugate acid. So if we actually use the Pka data, we see that this is going to be the stronger acid. And that's going to imply that the lone pairs on the oxygen are more stable than the lone pair on the nitrogen. And that implies that this reaction should be favorable, right? We're going to be running to the right where KQ will be greater than 1. We could support that also using structural analysis. So if we look at just the lone pair on the nitrogen here, nitrogen is less electronegative than oxygen. They're about the same size. No induction or resonance in either of these two structures. So we would expect the oxygen lone pair to be more stabilized. Same prediction. Finally, we could look at carbonyl electrophilicity. So we have an ester versus an amide, and we know from previous sections of this video, as well as our work in Unit 4, that amides are far less electrophilic than esters, which means that the reaction going to the right is faster than the reaction running back to the left. All of those things all suggest that KQ for the SNAc reaction will be greater than 1. So you can see that the analytical process for these protic neutral nucleophile reactions involving, or in SNAcs, it looks exactly the same as what we've done before. The key, or the trick, I guess, is to make sure that if you do use the pKas, that you actually are using the correct values, right? Those of a conjugate acid, not the structures themselves, which you probably have pKas memorized for, and therefore it would be easy to fall into this kind of confusion. We're going to construct what I'll call a stability ladder, where we look at different kinds of carbonyl electrophiles, things like acid chlorides, or thioesters, or esters, or carboxylic acids, depending on what R is, or amides. You get the idea. And if these compounds were to react in a SNAc reaction, what would the leaving group be? So we see for an acid chloride, that's always going to be a Cl- anion. For a thioester, it's always going to be a thiolate anion, and so forth, and so on and so forth. What I've done is actually sorted these electrophiles such that the most electrophilic is at the top, and the least electrophilic is at the bottom. So in other words, our electrophilicity is dropping as we go down this ladder. On the other hand, if we look at these different anions, you could convince yourself, and actually through the examples in this video, we've done most of these possible anions at some level, that this Cl- is the most stable anion, and this nitrogen species would be the least stable anion. We could also convince ourselves that this is true by looking at conjugate acids and pKas. So let's add that. We've got our conjugate acids, pKas for those conjugate acids. So for Cl- it would be HCl. For this carboxylate, it would be a carboxylic acid. For a thiolate, it would be a thiol. For OH- or OR-, it would be water or an alcohol. And for or NR2-, we would have an amine of some kind. So those would be our conjugate acids, and we can actually add the pKas now. So HCl is -6. Carboxylic acids are around 5. In fact, we'll just say these are all approximate. So 5. Thiols are somewhere between 7 and 10. We'll say 10. These are around 15. Water is 14, so close. And then an amine is about 35. So we can see that the most stable anions at the top, and our least stable anion at the bottom. This is going to be helpful for us because what we've basically done is created a system where we can go from this electrophile to anything below it in the table, and that will be a favorable SNAc reaction. So another way of saying that is that any SNAc that trades the carbonyl higher on the ladder or one lower on the ladder will be favorable. We've essentially done the work in this video to understand why this statement would be true, but now we can encapsulate everything we've learned into a quick reference. We know that acid chlorides are the most electrophilic, so basically anything that they're going to react with is going to end up that makes any of these other things, and these other things are less electrophilic. We know what that means for SNAc favorability. Same thing could be true for looking at conjugate acid pKas or anion stabilities. So this can be helpful as you work problems to kind of have this general ordering in mind. And we'll actually use this kind of general ordering of reactivity again in Unit 6 for different kinds of reactions. So the next video of the series, we'll be tackling a few kind of specific SNAc reactions that have either like added reagents or that look really different from a general kind of a SNAc process. And in particular, we'll deal with a conundrum. How is it that we can ever get an acid chloride if it's at the very top of the ladder?